We can come across people in the history, all those successful people had a failure in their book history, but they never gave till they become successful. Universal intellectual trust is the blessed platform for the students to showcase their talents and discover the best within. Every activity of the Universal Intellectual Trust would help the students to walk one step further in finding the best of talents a student is blessed with. We, the Universal Intellectual Trust family, at our fourth webinar on sustainability through thermoelectrics. We feel deeply cherished to offer a pleasant welcome to each one of you as you are the beam of support for all the efforts taken. Welcome you all. Tiny seeds make boundless harvest. Drops of rain compose the showers. Seconds make the flying minutes, and minutes make the hours. I invite our greeter Dr. K. Rajkumar, UAT Secretary, to address the welcome note and guest introduction to this October gathering.
I welcome one and all for our UIT webinar. It's the fourth webinar we are conducting. It's a scientific work which we are interested to do this one. So our Universal Intellectual Trust is interested to promote and enrich the scientific ideas for the audience and the each and individual person. So our teamwork is a successful one for our today's progress. So our chairman, Dr. A.S. Ganesh Raja, who is a person who did a PhD in Pondicherry University and he completed his postdoc in Dalian Institute of Physical and Chemical Science in China, and myself, Dr. Rajkumar, to complete a PhD in the same university. And after that, I am in the Central University of Tamil Nadu as a assistant professor on contract faculty. And Dr. Chandrasekhar, who did his PhD in IIT Madras, and he got a postdoctoral fellowship in China, Ceylon. So that's our board of members who is the initiator for this overall process, and Dr. Y. Shashikummar and Dr. S. Tirumurugan, who are the kind fellow for helping for our Universal Intellectual Trust. Dr. Shashikummar completed his postdoctoral fellowship in more than three countries, including the Brazil and China and Korea. And Dr. S. Tirumurugan is a assistant professor in National College, Trichy. So, and addition to that, volunteers, those who are helpful for our UIT trust, is a supportive one. So, this is the first seminar which is done by, which is completed by the Dr. K.T. Varghese from the Bangalore. He given a good speech about the turning an idea into a patent rights. So, and this is a second seminar which is given by Dr. A. Shobin, a wondrous world on one dimensional material, who is from SR Music Tiruchirappalli. And third one is missing. So third webinar is based on the robotic representation by the Balaji Thiru. He's a founder of Village Robotics, and he's a person who interested in the robotic systems and future robotic ideas. He given in the third webinar. Right now we are in the fourth UIT webinar on sustainability through the thermoelectrics. So Dr. Karthikeyan Vaithinathan is going to give his presentation. Before going to that, he's a qualified person in MTech and PhD. So MTech in Pondicherry University in the Madanjit School of Science, Green Chemistry and Nanoscience. So he did his MTech in Pondicherry University under the Professor Tilagan from Pondicherry University. And after that, he come to the IIT Madras at IIT Bombay at 2014 as a research assistant. After completion of that one, he got a position in SRF. Got a position as a SRF in Anna University, Chennai. And next to that one, he went to International Advanced Research Center for Powder Metallurgy and New Materials, which is in Hyderabad. He got a position as a postgraduate researcher in 2008. So after that, with the wonderful experience, he got a position as a PhD fellow as in University of Hong Kong, which is a world prestigious university. He got a position in that one, that record of Dr. Vaithinathan. So there's a research assistant, senior research fellow, and postgraduate researcher. After the PhD, he completed two postdoctoral fellowships and the assistant, including the teaching ability. He got a wonderful experience in this research field, and he got so many awards related to the Research Talent Hub, Innovation and Technology Commission Fellowship, and government, which is given by Government of Hong Kong, Outstanding Teaching Award in Hong Kong, and CAS Devan's Presidential Fellowship, and National Renewable Energy Fellowship. So these are the awards and fellowships he received. So there's a research team, and he worked under the major title as a thermoelectric material and devices and the materials, which is based on the waste heat recovery applications. He got two options, and one is the industrial collaborative projects and the academical research projects. Based on these introduction, he having a good experience in the research field. So in the teaching experience, he got a position in the Hong Kong City University of Hong Kong, the various titles, ceramic, ceramics, outstanding teaching awards. These are the highlighted one from his resume, and he also mentoring and scientific activities, which is hopeful under the various sector in the Pondicherry University City Union of Hong Kong, and reviewer. These are the additional interesting profile. And finally, Dr. Vaithinathan got a 13 highly reputed journals. So based on this, among these, topmost journal is Journal of Power and Sources, with the impact of 18.5, and Journal Cleaner Productions and the Advanced Materials. These are the highlighted research publications which he given for scientific community, and the book chapters and his thesis, which is based on the thermoelectric materials and the thermoelectric cooling for a construction of solid states air conditions in lift. Our profile got a good research activity with the additional supportive teaching experience, and he also finally concluded with a list of patents which is based on the variable thermoelectric device, which is an upcoming field. So we are heartily welcome our chief guest, Dr. Karthikeyan. To welcome you, Karthikeyan. So, hello, what do you think?
Hello? Yeah.
Hello,
Yeah, it's audible. Hello?
okay.
Yeah. So,
So, a hearty welcome for our research team. In addition to that, Karthikeyan Vaithinathan is one of the coordinator for our UIT trust. He given wonderful ideas to promote, to enrich our UIT also. So once again, I thank you for that also.
thank you.
Karthikeyan, you can share your slides.
Okay. Hi. Hello. Good evening, everyone. I think I'm audible to everyone.
Yes, yes.
Yeah, so today we will have a webinar on the topic of sustainability through thermoelectrics.
Excuse me,
This is my.
Vaithinathan, can you unmute your video, please?
Okay, sure.
Please. Yeah, yeah. Thank you. Yeah,
Please share it as a full screen.
Okay, sure. Visible, right? Right now? Hello.
yeah. Yes. It's visible.
Yeah. Yes. Okay. Let's. So today we will have this webinar on the topic sustainability through thermoelectrics. This is my research work in the past 5 to 6 years. Um, it is all about fabricating and discovering new materials for thermoelectrics. Uh, and actually, it was going to make this personal more interesting. So here, thermoelectric in the sense like some semiconductor materials are capable of generating electricity when heat is applied to the material. I mean, so as let's stated in the first slide, you can see the demonstration. It is the effect is called the Seebeck effect, and the reverse effect is called Peltier effect. When the semiconductor material,
That
when the
again
semiconductor
is not a full
material,
screen.
it's not a full screen.
Share a
Hello,
full screen for that.
it's full screen, right? Okay, let me stop sharing and share the. Okay, now it's a full screen, right? You get it? Are you able to see the full screen?
Yes, sir.
Yeah. Okay. So the topic is thermoelectrics. I mean sustainability to thermoelectrics. Here, thermoelectrics has two effects, which is Seebeck effect and LTR. Seebeck is when we apply heat to one end of the material, the charges in one end pass just to the cooler end, thus producing a voltage inside the material, which is called the Seebeck voltage. Using this effect, we can utilize the heat, waste heat from any source and generate electricity. This effect is called Seebeck effect, which is for generating power, and the other reverse process is called the Peltier effect, which is mostly used for cooling like refrigeration and stuff. Here, what we do is instead of giving heat as input, we give electricity as input, and in the opposite end, we have which is a cooling effect. It's like it can reach 100 minus 50 degrees. This effect is called Peltier effect. So this is general introduction. I will go into details of how it is actually works and how we implement it for thermoelectric. So why we need to do thermoelectric work? Actually, if you see today's world's energy requirements, primary energy source comes from thermal power plant, nuclear, and incineration power plants and natural electricity. Right? However, we use the power from these sources Only about 34% of the power produced from this power plants are used for any application. For example, household application, industrial application. Any instrument uses only up to 34%. All the remaining 66% of the electricity produced is wasted through cables to transfer or through the instruments we use or in any form. This is the efficiency. Since the efficiency is very low, there you need to burn a lot of coal to produce more and more electricity, and still it gets wasted. 66% is still gets wasted. So when you see the total energy consumption scenario um, from 2005 to 2040 is still increasing, but but you know we are running out of coal. So to make a sustainability in the power generation system, we need to utilize this 66% of wasted heat using efficient materials and reconvert it into usable powers, which can be done through thermoelectric. So here, as I said before in the first slide, thermoelectricity is the direct conversion of heat energy to electricity and the reverse process. When you apply thermal energy in one point, it produces electricity at other point. I mean, in the context. And when you apply electricity in the material, it produces heating and cooling. So, so yeah. So the applications of thermoelectrics varies depending on performance of start, its application starts from aerospace to combustion engine. So the efficiency is determined by the factor called figure of merit (CT). When the CT number of the material is higher, the
Excuse me,
efficiency.
Dr. Vaithinathan. Slides
Yeah,
are not changing. I think slides are not changing because we are seeing
is it
only
changing?
your first slide. We are seeing your first slide now. Please,
Oh,
please make sure about that.
okay, sure. Yeah, can you see now the slide 15 is
Yeah,
moving?
yeah, yeah. Now it's moving. Yeah, please.
So now,
Yeah, yeah. Now it's moving.
oh, okay, okay, yeah. So the first slide I introduced, and the second slide is this one, introduction, the motivation to thermoelectrics as the primary energy sources are thermal power plants, nuclear power plants, incineration power plant, and natural gas, where we are getting power to our houses and industries, where 34% of the produced power are only used and 66% are wasted as heat from the cable or any other instruments and devices. So we need to retrieve the 60%, 66%, reuse it, and create sustainability in the power production. Okay? So we go for thermoelectrics. So just on I explained before. And the material's efficiency is determined by the factor figure of merit (CT), which which says the efficiency of the material. Okay? It means that, for example, we give a 60 degrees centigrade heat to the material. Imagine it can generate 60 milliwatt of power output. That
Sir, again it's not moving. Your slide is again not moving. It's not changing.
okay, sorry, then I
I
should use.
think yes, sir.
I will use
Yeah,
the
and
full,
that's why
full.
it's good.
Yeah, I will not use the full screen in this program. So okay, yeah, now I'll go with it.
Thank you, sir.
Here, uh, tell me. And application. Now you can see there. I repeat it. Sorry, the fault will not happen again. Okay. So applications of thermoelectric depends on the ZT of the material. ZT is the figure of merit, and every different materials have different CT, which is the efficiency of conversion from heat to electricity. When you see the application of thermoelectrics, it varies from it's used from a long back, like To be frank, give an example. If you know the Deep Space Explorer Voyager 1 and Voyager 2, they are still being powered by thermoelectric generators because as we go deep into the space, there is no solar energy available and no light available, so photovoltaics are not able to be used, and only source is to use the heat. So they use the I mean, nuclear radioisotope powered thermoelectric generators, where the radioisotopes deliver heat to the material and it produces power. So, so it was used in the spacecrafts. Right now, we are trying to use efficient materials for our daily day-to-day activities. Like, for example, heat is everywhere, right? Even body heat is a heat. You can use the body heat to generate electricity as well, like in the for I know a commercial product called Matrix watches, which produces power from the body heat and powers the watch. You don't need to charge the watch, no smartwatches for any time. It will run only from the body heat. That's one example. And the figure of merit one it's used for reliable source, and 1.5 it's for the material with figure of merit 1.5 is required for automobiles, and with 2 are required for solar generating power, solar thermophotovoltaics. And yeah, based on the ZT, it's used for different applications. That's what I like to say. The below figures are various applications of thermoelectric generators. Right? So, how the figure of merit is determined? That's one question. Like I said, Seebeck effect, right? Seebeck effect is determined by the factor S, which is called the Seebeck coefficient. It means, for example, you have a rod of an iron rod, and you apply heat in one end and measure the voltage change in both the ends. It determines the Seebeck voltage at that particular temperature. To be clear, we apply 100 degrees centigrade in one end of the iron rod, and the other end is not going to be 100. The heat travels from the hot side to the cold side. So, the same way, the electrons from the hot side get excited travels to the cold side. When you measure the voltage in both the ends, it will be higher when compared to in the room temperature condition because the electrons are getting energized and they start to move and produce the voltage. And this is what we are using for many applications. And this voltage varies from material to material. Now I gave an example, simple example of iron, but iron is not a thermoelectric material. Most of the thermoelectric materials are semiconducting materials with narrow bandgap. And figure of merit is determined by these three parameters, which is the Seebeck coefficient, electricity, electrical conductivity, and thermal conductivity. Okay, so Seebeck coefficient square times the electrical conductivity we call as the power source. I mean power factor, as I highlighted here, and K is the thermal conductivity, and T is the temperature we apply. Temperature difference applied. Temperature difference applied in the sense 100 in the end, and what is the temperature on that other end. That determines the temperature. And the efficiency is this formula, but it's complicated. Now, what I'm going to present is on how we develop the material. So, the main problem with the traditional thermoelectric materials are when you are trying to increase the Seebeck coefficient to get a higher efficiency, the electrical conductivity goes down. And when you are trying to improve the electrical conductivity and the Seebeck coefficient goes down. So it's these two are coupled together. So it's really difficult to decouple them and increase the Seebeck and say, electrical conductivity together. When you increase Seebeck and sigma together, the numerator value goes up when it remains the efficiency of the material goes up. That's what every researcher in this field is trying to achieve. And so that's what I'm showing in this figure. The ZT is relationship with Seebeck, electrical conductivity, and thermal conductivity. As I said before, we need higher Seebeck and higher electrical conductivity and ultra low thermal conductivity. Because when the thermal conductivity of the material, for example, iron, the example I gave you, when the thermal conductivity of iron is very low, in practical it's high, very low, then the applied heat in one corner does not travel to the other corner. So we are able to achieve a larger temperature difference. This is what is needed for getting a higher CP. Okay. The next, this graph tells if CVAC values are 10, what will be the expected electrical conductivity in terms of Siemens per meter. And that curve is the Seebeck coefficient. You can see the Seebeck coefficient value drops down as the electrical conductivity value increases. The blue line is electrical conductivity. And you have a point where the power factor, that is the numerator value, is certain. This is what everyone wants to achieve in the material. And here the N corresponds to the carrier concentration, number of electrons or number of holes in the material. And right now, in this work, what I'm demonstrating is how we decouple the Seebeck and the electrical conductivity. And there are many available techniques in the literature, like going through doping of doping of atoms into the material to increase the electrical conductivity. But it automatically reduces the Seebeck value. So we have tried a novel technique like introducing defects into the material. Like for example, if you mention about silicon, silicon wafers does not have higher electrical conductivity. To make them highly electron, highly conducting, we introduce phosphorus atoms into the lattice in order to achieve N-type nature in the material. And we, on the other case, we dope with boron to achieve N-type characteristic. For N-type is for phosphorus and boron is for P-type. So that is the process, doping process to enhance the electrical conductivity. But doping also have positive and negative sides. Like a dope, the composition of the material changes. For example, the percentage of deep phosphorus can affect on the other places. So we chose the non-destructive, non-doping techniques like defect engineering, and then lattice distortion, and hierarchical structuring, and phonon stacking techniques. So, uh, so what I'm going to show you today is how the defects in thermoelectric materials increases the efficiency, and with an example of zinc antimonide. Zinc antimonide is a new material with a high performance waste to waste heat to electricity conversion process. And we do the defect engineering in this material to increase the power factor, the numerator, and reduce the thermal conductivity to ultra low level through defects. And this is one of the example. And thin selenide is also another example. After that, I will show you how we use these two materials in our practical applications. And I also show you like using the body heat how we generate electricity to power our electronic devices. I will not bore you. I will go fast process. I think this shows a time scale from when the defect engineering is being employed in high numbers. It started early 18th to 19th century, and now it's in the peak because everyone wants to achieve a higher electrical conductivity for different applications like transistors and transistors. Here, we, I mean, most of the scientific researchers will try to get a defect-free material for a perfect performance. But in the case of thermoelectrics, we also need a perfect material, but it needs to be having certain distortions and certain percentage of it, right? To be a high performance also. So here, what is zinc antimonide? Zinc antimonide is a compound having 39 zinc atoms and 30 sp atoms in a unit cell, and space group is RC. It is believed that theoretically zinc antimonide has a phonon glass and electron crystal structure. This is a well-known concept. What it says is this material conducts heat, I mean phonons, like a glass. You know that glass does not conduct heat as a metal. So this zinc antimonide is believed to be sorry, zinc antimonide is believed to be uh, like a glass for heat and like a crystal for electrons. Like a crystal for electrons. It means that uh, crystal in the sense defect-free, a perfect metal, aligned atomically aligned metal layer to conduct perfect good electrical conductivity, high electrical conductivity. That's what this model means. And here, what we are trying to do is, even though this material possesses this property, their electrical conductivity is very low compared to the conventional materials. So what we try to do is we try to remove a zinc atom. The blue one is the zinc atom. We try to remove a zinc atom from the unit cell. Make it as zinc 38, and that's called a zinc vacancy defect. We need to replace zinc with something else, or we need to think about how to displace this zinc atom. So we used different material, different exotic materials like there are, the rare earth element groups, lanthanides and actinides. We use the lanthanide groups. They have different properties like high electronegativity and the atomic radius are also different compared to this transition metals. So we use rare earth dopants, intentionally introduce them into the unit cell of zinc antimonide and displace the zinc atoms. How we displace particularly the zinc atom is another question that we will be answering in the coming slides. And the uniqueness why we use the rare earth dopants are because they have F orbitals, whereas other groups does not have. This is the good advantage. Like they can do a different, can create anomaly in the material. So we want to try with the rare earth dopants. So we use that. And we found that it decouples Seabed and electrical conductivity and causes parallel increase in seabed and electrical conductivity. And also it creates defects in the lattice. It's a very dense defect which causes the lifetime of phonon to decrease. So, yes. So this is how this slide shows how we make fabricate the material. We take zinc atoms and then zinc metal and antimony metal powder. Then we add a certain percentage of rare earth dopants, and then do a high energy ball milling process, where these are mixed in the particular ratio, and due to the ball milling energy, they combine together and form this structure. And then we pelletize like here using the machine technique, spark plus machine technique, where the, met- the powders are compacted into a metal piece. It is compacted into a metal piece. It means that it has very high density and it's not like a powder. And then we go for the Seebeck characterization using the instruments, where imagine that the blue color rectangle is our sample, and So one this, and we apply heat in one corner. The red dot is the applied heat, and the other corner is left at atmospheric temperature. And we measure the voltage change in this circuit, voltage and current change. And this is for thermal conductivity measurement. This is a light flash apparatus where we shine the laser sample and get the heat output from the material through the sensors. Okay, the next slide is this one. Yeah, this is the characterization of diffraction. I mean, powder X-ray diffraction, where we see with different dopants. The dopants which we used are terbium and terbium, and we found the efficiency for cerium and terbium higher when compared to other materials. This illustrates the mechanism like we do the rarer terbium and the size of the
ஃபீட்பேக்
rarer
ஃபார்மு
terbium
அனுப்பிச்சி விட்றேன்
increases
வாட்ஸ்அப்பில் அதை இதில் போட்டுறியா
and causes the zinc vacancy defect. And here
செல்லுக்கு
the
வந்துட்டியா
thing is, this zinc vacancy
செல்லுக்கு வந்தா என்ன
starts to
செல்லுல
increase
இருந்து
as
மெசேஜ் பண்ண
the
முடியாதா
defect it's
ஆ
it's
ம்
charged, which causes the increase in the
ஆ
whole concentration of the
ஐயா
material,
ஆ
which is being observed in the hall
ஆ
measurement.
ஆ சரி
Mm,
சரி
yeah, here in the x-axis you see zero
ம்
point 0.1, 0.2, 0.3, right? It's the percentage of
வேறெல்லாம் ஒன்றும் இல்லை இதோ போயிட்டுருக்கு
dopant
25 பேர் இருக்காங்கல்ல
into a limited
என்னத்த
defect.
அதெல்லாம் சொல்லிட்டீங்க
Because
ஒன்றும்
you
பிரச்சனை
can
இல்லை
see that as the dopant percentage increases, the carrier
ஆ
concentration increases. If the carrier concentration increases, the electron
மிச்சத்தை நாங்கள் பார்க்குறது இருக்கட்டும் நான் 4 பேர்த்த உள்ளே வர சொல்லுங்க
and
ம்
yeah.
ம்
So this is
நான்
believed
வந்து
in
இது
hall plot.
நானுமே அப்படித்தான்
This
வந்திருக்கேன்
technique is used to determine the defect,
ம்
percentage of defect in the material. And here
ம்
we use,
சரி ம்
this is novel called atom probe thermography. This is used to visualize three-dimensionally that where are the dopants located. We use a sample of 10, less than 10 nanometer size, and then we use small piece of 10 nanometer and we reconstruct it, and we can say that how the dopants are distributed uniformly. The blue color is the CDM and the black one is the where the red and the blue one is. And another case is here, what is present? It means that when you dope any element into a lattice structure, it, it creates defect can be observed through the lattice constant changes. Concentration. The lattice constants A and C duration like starts to decrease, whereas for the highest concentration of zero point 0.5 it starts to increase. It means that after that 0.5% it starts to accumulate into a lattice. So we stop to determine that zero point 0.4 or zero point 0.3 should be the ideal concentration. So this yeah, we analyzed how the defects are formed in the material. This is the 10 nanometer tip I mentioned. You can see these are nano grain structures where circular oval shapes or individual nanograins in the material are detected. And the, this TEM image demonstrates the dislocation in the lattice and the zinc vacancies are circulated. Yeah, this is. I think this is for the defect understanding. Yeah. Uh, I want to explain here only this case, the photoluminescence spectroscopy, because this other thing is theoretical. And okay, um, yeah. In the photoluminescence spectroscopy, we can observe the defects formed in the material through the intensity change. Because when you measure the pristine material, you will have a particular peak, and when there are defects present, another additional peak formation or the intensity decrease, which means that the for, there are additional levels here, formation of additional levels in the material, which causes energy dissipation when it is trying to jump from the lower to more to the highly occupied. And yeah, this one is the theoretical, which I was explaining here. When you can compare the photoluminescence spectroscopy with the theoretical density of states, which are in the bottom below, which I have taken out. Here, this is the density of states for the undoped zinc and uranium, and this is for the cerium. You can see there is a sharp peak, that is the resonance peak in the edge of the valence band, which means that the concentration of holes in edge of valence band are increased by the dopant. But the cerium here is an electron donor, which means the compound should have been converted into an entire material, but it has not converted into an entire material and stays as a p-type material because of the zinc vacancy formation. And yeah, I don't think I want to explain everything here. It will be much more complex for industry students to understand. And yeah, we also performed the effective mass calculation at different temperature, and we can see how the effective mass of the material changes with different temperature. And what particularly I want to show you here is the density of states in graph 3, graph 3, which shows that there is a detached state, which means there is a formation of gap state. When when the electron or other carrier charges need to jump from one band to the other band, it just goes through the conduction method. But however, due to the formation of gap states, it cannot be through the conduction. Transport cannot happen through conduction process. There happens hopping, hopping in the sense of jumping of electrons from one band to the other instead of differential path. So this means that uh, during the hopping process, only the electrons can jump and the phonons will be split. So the thermal conductivity in the material will be drastically reduced. This is one of the technique to achieve the high CT in the material. And this is the Seebeck characterization. Yeah, you can clearly observe like the black one is the pristine one, and the other are dope cases. Black one for Seebeck, and whereas for the dope cases it keeps increasing. And also in the case of electrical conductivity, second graph, you can see that with the dopant it starts to increase. Of 0.3%. And this is the additional characterizations we done to prove that phonons are being filtered. We use the terahertz spectroscopy, which means uh, it's more advanced than the FTIR spectroscopy, where we shine the terahertz radiation on the sample and get the vibrational data from the sample, which shows the harmonicity. And the black one here shows the harmonic oscillation of electric lattice for the undoped phase. And whereas for the red, blue, pink, and the green, you see it's not an orderly manner, it's totally distorted, which means that the vibration pattern of this is totally disturbed by the tension that effect and creates anomaly. Way in the Raman are shown here, you can see the peak broadening happens, which demonstrates that the peak broadening demonstrates that intensity of reflected light radiations are being filtered by the defects. Also, this is the area where the intensity drastically drops with the dopants. Here I have demonstrated for different dopants. All demonstrates increase in values of vibration because the vibrations are being nullified by the defects of the material. Then, and this is the phonon mean free path observation. You see for the black cloud is having a higher mean free path of phonons, which means that the phonons can travel longer distance in the material and the undoped materials. After doping, you can see that they drop drastically, which means that the phonons are being arrested and not allowed to travel a longer distance, so the heat cannot travel longer distance. This both means the same. Yeah. So to conclude for this material, you can see the ZT of the doped material is very high compared to the black doped. So through the defect engineering and the novel doping technique, we observed highest CT at 670 Kelvin of this particular this capacity. Then we go for zinc selenide. I more interesting. And here, why I want to particularly show this material is this is the peak material right now, which shows the efficiency close to, I mean, the CT close to. The thing is here, unlike the like chunk formation, here it is like the layered arrangement. This gives another additional advantage like graphene and graphite. Electrical conductivity, electron transport can be drastically high. So, and the same thing I did here, but what I did was instead of doping in this material, I used radiation of alpha particle in this on this layers, which created latency of different units union to increase the electrical conductivity because the parent electrical resistivity is too high in megaohms. And with our effect formation technique, we achieve a higher electrical conductivity for and a higher efficiency. And the same effect of peak programming is observed for this structure. Here with radiation dose increasing from 50 to 250 micrograys alpha particles, we have demonstrated increase in the carrier concentration up to more than two orders. From, for the piston case, the order is 10 power 16, and for this case, we have achieved up to 10 power 8. Okay. So this also the electronic density of states calculation. Here, this is for the piston one, and with the defect one, you see the formation of gap state here, which is responsible for the pumping convention and reduction in the electrical conductivity. This is observed in the case of thin vacancy condition, not observed in the case of selenium vacancy. And then this is phonon density of states, which means phonon density of states, and this is the electron density of states. And when the number of states increase, scattering increases. For example, if you are walking through a cloud, it means that your speed will be decreased, right? So that your time for reaching to the other end also decreases. The same way, when there is the number of less number of times your speed is high, the phonon travels from one point to another very fast, and there are not many number of bands. Their efficiency is reduced and the thermal conductivity is really reduced. And the seabed electric current power factor balance. In this case as well, seabed electric conductivities are parallelly increasing. So that we get a maximum power factor of 10 microwatt per cent And then in the summary, the figure of merit of about 2.5 is achieved in my technical intelligence course. Depends on this one. Then we go for the. I want to show you the application just to stop sharing this. I'll also go with the same, not sharing these things. Oh, yes. Same thing. Yeah, one of the screens. Have a lot of. Are you able to see my screen?
Yes, yes.
Yeah, okay. So here, as I said before, we are losing that is 66 percentage. So if we are using the thermoelectric power conversion, we can do close to 100. So here what I am going to show is how I use my material for the wastage recovery from the heavy vehicle exhausts. You know the bus exhausts have a high temperature gas output. So we use the bus engine which has a flue gas temperature 320 to 380. And then this is the device which we fabricated. The device which we fabricated, which is using the zinc antimony structure. And this is the heat harvesting block. Over the heat harvesting block, we placed our thermoelectric generators and then packed them perfectly. And then we gave the we gave it for the testing at 350 degrees centigrade, and we got a good efficiency. I mean, used the hot air output for the power conversion. And this is as zinc antimony is non-toxic, we are able to develop non-toxic thermoelectric material operating high operating temperature, and this is lightweight, and you can control the number of power output they can do. As you can see in this structure, we pass the hot